Proportions summarize categorical data, and in the previous video, we explored the distribution of the sampling distribution of a sample proportion. Means summarize quantitative data, and equally important is the concept of the sampling distribution of a mean. In the previous section, we saw that if the sample size was large enough, and if you drew repeated samples from the same sample size from a population, and measured the sample proportions, which we called p-hat, we get for each sample that the collection of these sample proportions would pile up to produce a normal distribution. Amazingly, the same is true for the sample mean, x bar. This result is so important that it is referred to as the central limit theorem. It says that the distribution of any mean becomes normal as the sample size grows. We do not have to worry about the shape of the original distribution. Even if we have a skewed distribution, the central limit theorem tells us that the means of repeated random samples will tend to follow a normal distribution as the sample size increases. So here is an example. The sale of food and beverage for a small diner fluctuates from day to day. The mean daily sales is 900. The graph shows two distributions. The red graph is the day-to-day sales. It is the population graph. The green graph is the mean daily sales based on n equals 7 days. This is the sampling distribution of the graph. It is not the graph of individual sales, but the average of 7 days. There are several important things you should notice about this graph. The underlying graph of daily sales is not normally distributed, but slightly skewed to the right. The graph of average daily sales based on a sample of size 7 is approximately normal. Both the population distribution and the sampling distribution have the same mean, namely 900. And there is more variability in the day-to-day sales than on the average weekly sales. So some observations. Daily sales are not normally distributed, but average daily sales with n equals 7 is normal. They have the same mean, 900 rather, and there's more variability in the daily sales than in the So we saw that for large samples, the sample proportion for a fixed sample size was normally distributed when the sample sizes were large. But for proportions, the criterion was that both NP and NQ be at least 10. For sample means, the criterion is that the sample size be at least 30. There is also a dependency of the spread of the sampling distribution of the mean on the sample size. As the sample size increases, the variability of the sampling distribution will decrease. As the standard deviation increases, the variability will increase. There's a special name for the spread of the standard deviation of the sampling distribution of a mean, and it is called the standard error. The precise relationship between the sample size and the standard deviation is that the standard error is the sample standard deviation divided by the square root of the sample size. As you might suspect, the mean of the sampling distribution of a mean is the same as the population mean. So if we were to use the results from proportion to model the formula for means, the margin of error would look like the sample value times a z-score reflecting the confidence level and the standard error, which for a mean is sigma divided by the square. There are some issues with the central limit theorem. And what are they? Why is life not as easy as we thought it would be? The standard deviation of the sampling distribution of a mean is given by that formula, sigma divided by the square root of n. So if the sample size, and the central limit theorem only applies to large samples. So if our sample size is not large, the sampling distribution isn't normally distributed, and we cannot use a z-score. And there are many occasions when researchers conduct studies with sample sizes that are not large. The other is we do not know the population standard deviation, but rather only the sample standard deviation when we are conducting an experiment. So there's a fascinating little story about a man who made a really big contribution to statistics. His name is Gosset, and working in the late 1800s, Gosset had a job that was the envy of many. He was the quality control manager for Guinness Brewery in Dublin, Ireland. Gosset used small samples of size 3 and 4 since larger samples would not be healthy. He noticed that his estimates were off considerably, and this bugged him. So he took some time off to get a degree in statistics. So he found a way to deal with small samples and the problem of using the sample standard deviation by creating his own model, which he called the t-distribution. You might ask, why didn't he name the distribution the Gosset distribution? Well, Guinness carefully guarded their brewing secrets and prohibited any of their employees from publishing anything, even mathematical results. So he published his results under the name Student, and the distribution is now called the Student t-distribution. So what are the characteristics of the t-distribution? Like the normal distribution, it is symmetrical. But every time you change the sample size, you change the shape of the curve slightly. So there's not just one t-distribution, but a different one for each sample size. To give you an idea, the solid curve is the t-distribution for a sample of size 3. And the dashed curve is the standard normal curve. Both are symmetrical, but the solid curve is more spread out. There's more area in the tails. The student T curve does not follow the 68, 95, 99.7% rule. What is true is that as the sample size increases, the T distribution, the solid curve, gets closer and closer to the normal curve, the dashed curve. Today, few people use tables to look up t-values. We will be using an online t-calculator the same as we used an online z-calculator, and that would be the StatCrunch calculator. Since t-values depend on sample size, we will have to supply information about the sample size. The calculator will ask us for something called the degrees of freedom, abbreviated DF. The definition of the degrees of freedom is that the degrees of freedom is the sample size minus 1. So again, we will use StatCrunch to find our t-values, and we'll find it under the menu item Stat Calculators T-Calculator. So if we conducted a study of 20 subjects and we wanted to use our data to establish a 95% confidence interval for a population mean, we would enter the degrees of freedom 19, 20 minus 1, and the central area to be 0.95, and this is demonstrated on the next slide. First, we have to select between. Conceptually, this is written T with 19 degrees of freedom with a central area of 0.95. So we would set the area to be 0.95, and the calculator reports back that the critical value of T is 2.093. So here we have it. To evaluate a confidence interval for a mean, it's as simple as first calculating the margin of error, which consists of a t-value that depends on the confidence level. We use the online calculator for that, multiplying by the sample standard deviation and dividing by the square root of n. Then we're going to take that and add it and subtract it from the sample mean. The term TS divided by the square root of n is called the margin of error. So let's take a moment to reflect on the margin of error and what you would do to decrease it if it turned out to be too large. The best way of doing this is to increase the sample size. The bigger the denominator, the smaller the fraction. If you can't increase the sample size, you might try to reduce the standard deviation, but this is not always possible. The amount of variability in the data is what it is, and it's hard to change it without redefining your study. Finally, you could lower your confidence level. The lower confidence level would result in a smaller t-value, and that would reduce the margin of error.